little bit small, so we are pitching. So we are in our group. We are working on different aspects of modeling, search-based software engineering, machine learning, all these techniques applied to software engineering. Okay. So the first thing that drives all this research is automation. So we want to automate some tasks that usually are difficult to automate. So just to take an analogy, so the picture you are seeing here is how people were building cars in the 50s. So a lot of people working on these cars. The cars themselves are simple cars, not the same technology as we have now. And as I mentioned, mostly manual control. If we look how cars are built nowadays, so a lot of robots, very complex cars, but all with this. Most of the production is done with automatic. So how we move from this period to this period, we accumulated a large amount of knowledge. Okay? And this large amount of knowledge was produced by critical mass of researchers and innovators all over the world. And all this knowledge we didn't move directly from one to the other. So we have an accumulation of improvements during the time, and all conferences and publications and all this kind of thing. How this applies to software development and maintenance tasks? In fact, this applies if we are talking about what we call general purpose artifacts. Okay? So things that are interesting to a large amount or large communities. So we have more or less the same way we evolve. The evolution was almost the same. But if we look at domain-specific artifacts, so this is much more different. So let's explain what is the difference between the two. So general-purpose artifacts have broad user communities. So we're talking about programming languages, IDEs. We are talking about modeling languages. So all these things, almost anybody in computer science knows about these things, use them for most of us daily. So we have a lot of conferences, a lot of journals, we have papers, we have researchers, and all these people are producing this knowledge and keeping incrementing, adding to the automation of these things. But if we look at domain-specific artifacts, so we have limited user communities. For example, if we have a language to describe plumbing architecture. So we don't have that many people doing research on that, especially in computer science. And also, we could have also some libraries. So we have a lot of libraries, specialized libraries. And so there are some users of these libraries, but not like a broad community using the same library. And for the task also, for the general purpose artifact, we have a fixed set of tasks. Okay, so for example, in programming languages or IDEs, so we have debugging, we have code completion, we have refactoring, testing, and all this something. So people are working on the same problem, trying to automate these problems and so on. Whereas in some domain-specific artifacts, so that the possibilities of tasks could be much larger, and without the fixed set of problems on which people are working. So, for example, simulation certification with different norms and things like this, which are specific to these domains. So the first, it's not there is not clear separation between it. So sometimes we have things that are like domain specific, but we have to gather like more interest, broader communities, and some aspects move to one to the other, and sometimes we're doing, so for example, or everything that is done now on machine learning pipelines for neuroscience or for genomics or things like this. So they started like with few people working on this, and then we have like a general interest, government putting some money, and even computer science researchers working on these problems for these specific domains, and then we can move from one to the other. Okay, but for most of the cases, we will stay there. So with this limited community. So to illustrate my work today, I will choose like 3 examples of domain-specific artifact or task. So the first of them is how to test validate model for a given domain-specific language. Okay, so suppose we build a domain-specific language, how to ensure that models that are written using this domain-specific language are valid, for example. Another problem is how to automate model transformation between 2 DSLs, between 2 domain-specific languages. So if I design a model in one language, how to automatically generate a new model for this second language. And the third example that I will go through is how to ensure the correct use of a specific code library API. Okay, so we could have some specific APIs and how we could automatically validate that a client is correctly using that. So I just first explained the general idea of using genetic programming with the examples, and then move to these 3 examples and show how we could use genetic programming in a straightforward way, but what are the problems that we have to solve, and then do some sophistication to use correct genetic programming. Okay. So the first thing, we have two like important notion. We have examples and we have learning. Okay. So the first thing is how to obtain examples, and then how to use these examples to learn the artifacts. Okay. So how to obtain examples? Usually we have 3 situations, more or less. The first one is we already have these examples in the past, so we collect them. So for example, if we take like in avionics, or you have people working, doing simulation, modeling, and then moving to simulation. So they already documented some past examples and some past, although they did this manually. Okay, so this is the kind of examples when they exist, we collect them. The other way of having examples is sitting with domain expert, and asking them to explain to us through examples what are the different situations that can occur for this specific task. So usually people use like you have A and then you have B and you connect N and B, and this is equivalent to creating this with A and B and so on and so forth. So this is what we call the typical examples. The third thing is, for example, for many domain-specific languages, if we have the description of the language, so we could automatically generate some examples with some coverage criteria or things like this. And then once we have these generated automatically, I will explain this notion of labeling later on, because in many situations, examples are not just a collection or artifact, but sometimes we have like more than this collection. We have to label these examples depending on the kind of task that we want to perform. So this is how to obtain examples. And then once we have the examples, the idea is to, starting from the task, we will try to explore the space of possibilities, of possible solutions, guided by these examples, by the conformity to these examples. Okay. So let's show some examples of examples. So this is for example, for model test validation. So if we sit with an expert, domain expert, and just generate examples, for example, and asking him to say if these examples are valid or invalid. So the labeling is just simple labeling. So for each example, model example, for example, say, okay, this is a valid. Oh no, this does not work. Okay, and we just label the models as valid and invalid. Okay, so this is kind of labeled examples, but simple labels. We could also have some complex labeling for the example. So let's think about transformation. So we have a model and we want to transform it, describe it in a language, and then we want to transform it in a model of a logic. So the examples are models and their transformed equivalents. So the labeling is more complex. So if we generate these models from the source language, so we have to produce these equivalent models in the target language. And the labeling could be even more sophisticated, like tracing which part of the models correspond to which other part of the model. Okay, so this is some complex labeling. Then we could have in some cases we don't need to label. So for example, if you are talking about how to use an API, so what we need is like execution traces of clients using this API. So we have already some clients using the API. So we just execute the clients on the API and collect the execution traces. I will explain which part of traces are of interest to us. And we don't need to label them. We just need to have these execution traces. Okay. So this is about how to obtain examples. Now, how to move from examples to knowledge with the objective of automation. So the knowledge is a solution in the search space. So we are searching for a solution inside a space of possibility. And the quality of a solution in that space is measured by the conformity with the examples. The more a solution conform to the examples, the more it has a chance to be selected at the end as a solution. Okay, and then the exploration, as we are using genetic programming, so the exploration is an evolutionary strategy where we try to generate a solution from existing ones and evaluate how the solutions will come. So the things that is different from classical evolutionary algorithms is that we need executable artifacts, because when we talk about software artifacts, so we need programs, rules, constants that we could execute. Okay, so and this makes things a little bit more complex than, for example, finding a configuration, finding whatever some problems when we use evolutionary algorithms. The second thing is the artifact that we are trying to learn are complex. This is not a classification or a regression problem. So we are trying to learn programs, complex programs with semantics and things like this. They must conform to a certain syntax. They need to be well formed. They need to be to have a semantics and so on. So this is very complex. And for this artifact, the input-output are themselves complex. So if we are talking about model transformation, so the input is not like a numerical vector. This is like a model with typed nodes and relationships, and the output is also, in some cases, something that is complex. So this makes the problem worse, how to learn something that is complex. And this is why we use multi-objective optimization to try to control all these complexity. So for the multi-objective, because we have more than one objective in general. So the main objective in general is the conformity with the examples. Okay, so So this is the main objective in all the problems that we are trying to solve. But we have other non-functional objectives, such as the consistence of the solutions, because this is a known problem, a developing problem in genetic programming, where solutions tends to become bigger as we evolve. Okay? And we have to control this size of the solution, but also well-formadness. We could have different aspects of these programs that we want to control. So as we are trying to manipulate programs or life, and we have multi-objective perspective, so the best solution to use is multi-objective genetic programming. Okay, this is how it comes. Now the today question, as soon as we are talking about learnings, why not to use machine learning or deep learning? So we have many reasons not to use machine learning or deep learning. So the first reason is the amount of data that we have. Okay. So in learning from example, learning artifact from example, we do not consider the examples as examples and try to infer something that is more general. So we consider examples as specifications. Okay. And so our goal is not to avoid overfitting or such kind of problem in machine learning. So we want to find artifacts that conform to those examples at hand. But examples are not that many, and using machine learning or deep learning for this complexity or artifact to learn is not obvious when we have these very few examples. The second thing is, even with the state of the art of machine learning today, so we have a lot of advances, for example, in robotics, but they are still struggling with sequence of actions that the robot has to perform. So this is like a very limited space of possibilities, but they are still not having like 100% results for this kind of thing. So research are still going there, and having like executable code with some complexity, manipulating like complex input output. We don't believe that this is doable, especially with kind of examples that we have. So these are some reasons for which we use genetic programming rather than machine learning or deep learning. We believe that we are going to that at some moment, but at the state of the art today, we're not allowed to do that. So multi-objective genetic programming is some sort of a mix between classical genetic programming, like mono-objective genetic programming, and multi-objective optimization. So the classical genetic programming is we start by an initial of randomly created population of programs, then we execute each program on the examples and evaluate the fitness of this program on the basis of this example. If this evaluation gives an interesting and criteria, match some interesting and criteria, then we just return this best program. Otherwise, we just derive new programs from these current programs using some operators, replace somehow the current population by new one, and then go do this cycle until we reach some end criteria. At the same time, multi-objective optimization, this is an example of one algorithm, which is NSTA2 that we use, non-dominant sorting algorithm. So we start with a population of solutions, okay? Then we generate using genetic operators another half from this initial population. Then we sort the solutions in front. As we have many objectives, so we use the notion of dominance. So a solution dominates another solution if it has at least equals value for all the objectives, and at least one of the objectives it has a better value. Okay, so we don't have like a complete order because we have many objectives. So in each front have solutions that dominate the other front, and so on and so forth. And then we cut the set of solution into two parts. We take the best ones. And if we have the cut point inside one front, we use what we call the crowding distance, which is a diversity measure. So we want to take a sample of these solutions with the remaining number to fill and as diverse as possible. So we use some sort of crowding distance, which measures the position of the solution with respect to the others using the object. Okay. And then we iterate, we take this hard, come back here and iterate and so on and so forth. So multi-objective genetic programming is a mix between the two. Okay. So we are manipulating programs rather than solutions, and we have more or less the same. Okay. So now how to move from this generic process to specific problems as ones that I mentioned earlier. So we have to define what is the search space, okay? Because are we for example, if I'm looking for transformation, so using like a transformation language like ATL, for example, the space of solution is any solution that I can write in ATL language, and that manipulate the elements of the source and target languages. Okay? But this can be huge. So sometimes I have to define my search space. Okay. So once I define my search space, is how can I represent the solution inside the search space. So what is the encoding of solutions, and how to create an initial population to start my process. Then the other thing to define for a specific problem is how to derive new solutions from the existing ones. Okay. What are the genetic operators? And the genetic operators will depend on the encoding of the search space. Okay. And then I have to define how to evaluate the solutions. So these are the objectives I mentioned earlier. So the conformance to the examples is one of them, but I need to define other objectives to ensure some non-functional properties of the solutions that I want to learn. And finally, I have to define some search strategies and parameters that are specific to this problem. So I will come back to these considerations for the kind of problems that I mentioned. We lose some time. So I guess I still have like 20 something. Okay. So let's start with learning well from these rules. This is to assess if a model is valid with respect to a domain-specific language, for example. Okay, so usually when I define a domain-specific language, so I define like what is the structure of the programs that I can route or models that I can write with this language. Okay, so this is what we generally call a meta model. This is an example of a simplified version of the state machine meta model or the state machine language. Okay, so I have vertices, I have transitions, I have pseudo-states, and in pseudo-states I have a join for final simple state and so on. Okay, this is a description of my language, descriptor of my language. Then I can build this kind of models using this language. Okay, but if I write this model, okay, it conforms to this description, but it is not valid because for example, I need to have 2 outputs. For a join, I need to have 2 inputs. So how to ensure that that a model like this should be validated with respect to this? So I have to add what I call well-formalized rules. Okay. This is OCR rules. Let's say if I have a 4, okay, so the size of the outgoing edges should be greater than 1. Okay. And if I have a join, so the size should be of the common edges should be greater than 1, for example. Okay, so I have to add this well-formed truth to complete the description of the language and ensure that the models that I can write will be valid. Okay. However, writing this, so this is a simple one, but for many domain-specific languages, we will have many of this. This is formal language. OCR is not easy to write for non-computer science people. And so the idea is, how can I learn this just by having some examples of valid, invalid models with respect to this language, for example. Okay, so this is one thing that I can do. And we did this some time ago about learning these well-formed rules using examples of valid and invalid. Okay. So in this situation, what we did is the search space is any OCR expression that involves constructs from the meta model, defining the domain-specific language. Okay, so this is how we are code. So we have a set of invariants, OCR invariants. Each invariant is defining a well-formed truth. Okay. Then we use like classical genetic operators like crossover, where we have like two sets of invariants, and then we create offspring by just swapping some invariants from one solution to the other. Okay, so this allows us to build new solutions, and we have some mutation operators because by doing only crossover, we are just recombining the genetic material that we produced in the initial population. So we cannot just rely on crossover because we are not sure that all the genetic material is already in the initial population. So we use mutation to inject some new genetic material, and we could do it at the invariant set level when we could add a new invariant, delete an invariant, for example, or combine two instances with implies. For example, we have one invariant implies another invariant. At the invariant level, we can do many things, changing the comparison operators, changing the logical operators, and so on. So we can modify anything in the description of the invariant. Then for the objective, so we will see the classification accuracy of valid and invalid examples. So if I have a candidate solution, I just feed the models and see how the solution is able to discriminate between valid and invalid solutions. And also I have to be aware about size, because in our initial work, so that the invariants could become like large and large, and some of them does not mean anything. So we have to control somehow the size of the invariants. And so we had this first paper, we got interesting results, but then we tried to do some complex things, and we found like some problems. The most important problems for the learning was one of the two most important problems is the large space, because any OCL expression involving any element of the meta model, this is like an infinite set of possibilities. So the chances to converge toward the good ones is very small because of this. So what we did, we looked at what exists in the literature, and rather than creating randomly this invariant, in fact, we use patterns of invariants. So we did some work with Tadavid Houari. During his PhD thesis, he took a lot of languages with their well-formed rule and tried to find patterns. Okay, and he found that any of these well-formed rule can be expressed with a limited set of patterns or combination of these patterns. So the problem changed. So the search space is no more find any OCL expression, but rather find instances and combination of instances of these patterns. Okay, and this changed a lot the results and the convergence. Okay. A second problem that we have in general in genetic programming is what we call single fitness field. So this happens. I will give an example to explain this situation. So suppose we want to learn an arithmetic expression, okay, that takes like two inputs and produce one output. Okay, so these are simple values, and I have a set of examples. Okay, so I have this set of examples, and the idea is what is the arithmetic expression that produce this output starting from this input. Okay, so one possibility is to say, so this is C equals to A plus B, and it works every time. Okay, 100% fitness, this is perfect. Now imagine that we have a fifth example. Okay, so this does not work now because this fifth example contradicts this solution. Okay, so in fact the solution is this one. Okay, at least for these 5 examples. Okay, but what happened during the evolution? Okay, during the evolution, I have my solution, my population of solutions. I have the examples, and green square means that the solution resolved this example. Okay. The arithmetic expression works with this example. Okay, and then I start my evolution. Okay, I start my evolution, and I come to this situation where I have a lot of them having like this 80% conformity. Okay, and I have some with 6 and one with 0.2, 20%. Okay, and if I rank them, so I have these alphas, okay, that have like a large fitness value, and I have some of these solutions like this one that have very small fitness value. And what happened during the evolution? Usually, as the fitness is low, so I will just ignore it at some moment, and all my population will converge toward this, and I will have the wrong solution at the end because this was not supposed to be the good solution. Okay, so how to solve this? So in another work, we introduced the notion of social diversity, or social semantic diversity. So the idea here, so we were inspired by the TF-IDF. So when you search a document on the web, or so you have TF, which is the term frequency. So the document that contains the terms that you are searching will be selected. But we have the inverse term frequency. We give more chances to solutions that contain terms that the other solution does not contain. Okay, and we did exactly the same. So if solution 0, for example, that solve only one example, but this example is not solved by the other solution. So we boost the fitness of this solution just to ensure some diversity in our population. Okay, and so we give more values to, as I mentioned, solutions that solve examples that are not solved by them. So we define a new metric that we add, and we can. Houari is the author, one of the author of this. They probably had some. Should I? Okay. So Houari comes just at the moment I'm talking about his work. Okay. So when we tried this idea of diversity for the performance tool learning, and we tried in 2 different configurations. You remember when I showed the process of multi-objective genetic programming? So we added as another objective with the conformity and the size, or as a crowding distance. So we don't use it. We use it only when we have a front and we have to take part of this front. Rather than using the classical crowding distance, we use this social diversity as a crowding distance. Okay, and as you may see, so here we have the number of generation, the best solution, how many generations it takes to find the best solution, which gives you an idea about the convergence. And in blue, we have the accuracy of the solution. And if we look at without this social diversity, so usually it takes a lot of generation to find the best solution. And we don't have some uniformity in some cases. So these are two different problems, different languages. Whereas as the crowding distance, we have better results than even with objectives. So each time with crowding distance, the convergence is very fast, but also the quality of the solution is very fast. So these are different executions, I guess 100 execution. And we try to see how these 100 execution, what are the quality of the solution that they produce, and what is the distance. So as you might see in both cases, we always have better conversions and a higher accuracy of the solutions when injecting the social diversity. Yeah, something that is interesting also is the sensitivity to the execution. You know, when we are using genetic programming, this is a probabilistic algorithm, and so we don't have the same result for each execution. Okay. So without the social diversity, so these are different runs, and see how each runs, what is the best solution for each generation. So we look at the evolution, and we see that there is no uniform evolution. Okay. With the social diversity as an objective, so we have a better situation. So most of the solution converge somehow quickly, and we have some that converge later. Okay. But with the crowding distance, the convergence is very fast, and we have almost the same behavior except for one or two executions. So which is a good result. Now, this is for the first problem. So for the learning model transformation, this is the second problem. I will go through like the same one very quickly how to do it, and then what are the problems and how to do it. Okay. So why learning transformations? Okay, so I show some examples with like a UML diagram transformed into databases. So we have textbooks, we have everything about this. So we don't need to learn these things, we already have them. But if I take the analogy with natural language translation, okay, if we are translating from French to English, we don't need to do anything. We just like Google Translate and then translate. So like you have this French expression, and tiens, bon Dieu, que Dieu tu l'auras, and then you then search it on Google, and you have this, a bird in the head was in the bush, which is completely different. The words are completely different, but the meaning is the same, which is very sophisticated translation. But if I do it for some regional or minority languages, I don't have any translation. Okay, so I have this expression in Kabyle, which is a language in North Africa, and this meaning more or less meaning when donkeys hear turns gray when they get old, which means this does never happen. The animals here don't turn like humans, and the equivalent in Inuktitut is when crows are white. Okay, and these are different. Okay, so I cannot rely on the general community knowledge producers and translators. So I have to do something by myself or help people, this small minority doing this kind of thing. So this is why in some domain-specific languages we need to help people automating this transformation. So the learning principle is the same. So we have examples. So we have these input and outputs of the transformations, examples. We have many of them. And then we have the same process. So we have search space, conformance with the examples, and find the model transformation that better conform with the example. I forgot to mention, we are not automating things. These are all for recommended systems. So because we never know that something is perfect, okay? But we have to understand it as something that we recommend. So here, same solution is a set of transformation rules. So we have some rules. Each rule has a source pattern, a target pattern, and the source pattern is some generic constant from the source language that produce some generic constant from the target language. We have some join statement and binding, taking some values and putting them in the instance of these values. So this is more or less the transformation. But the rules are like this. So this is a JS language, but it could be any language, rule-based language. So if we have a superclass, a class that inherits from another class, and we have the names of this class, then and an attribute of one of the class. This attribute become like a column, for example. So, okay, this is kind of rules that we have. Same thing for the crossover set of rules. We just exchange the rules between the sets and some mutations at the root set level or at the root itself to introduce some unique material. And the objective is comparing the expected and the produced models. Okay, so each time we give the source model to a solution. This solution generates a model and we compare it to one of the examples. And we have like some matching maximizing full matches, so rules that exactly match the others. Except partial matches, sometimes we have a rule that suits them another tool or and try to minimize the no matches. And we also try to control the sets of them. So thinking. Some limitations, so inconsistencies within the example. So when we have the examples, sometimes it seems that in one example, the source gives something, and in another example, the source gives another. So we have to manage this inconsistency. And this is an example. So we have an association between two classes. In one case, it creates a new table. In the other case, we don't have this table. And the difference between the two is the properties of this association. So we have many to many, and we have one to many. Okay, and so we have to deal with this situation. Sometimes it's even more complicated. So we have a one-to-one between two classes. In one case, we create a table by concatenating the two. In the other case, we just have one table per class and some only between the tables. So what is the difference between the two? Why in this case we have this one and the other case I have a different one? In fact, this depends on the content. So if you look at address, it does not have other association with other classes than this one, whereas employee have different associations. So at least this is something that is not easy to learn in the search space because you have to deal with a lot of conditions. Another thing that is even more complex is that the rules that we want to learn, usually in model transformation, the rules is if you find this pattern, you have to create this pattern. Okay? And creating this pattern just instances and giving the values. But if we want to do something like this, so we have a table here, we have values, and then we transform these values into size of these parts. Okay? So this is not normal, this is not equal. This is a rectangle that we have to create and assign a size. And this size physically is not the same value as this because we have to display it. So we have to find a way of calculating the proportion of this with respect to all sum of the values. And this is more complicated. Okay? And by having this, the search space become like almost infinite because we have any combination of string operators, arithmetic operators, some functions that they can call, and so on and so forth. How to deal with this? So we came with a new way of doing this. Rather than just using this one step, I give examples, I have the search space and I produce a solution. So we give this multi-step learning to solve these problems like one step at a time. So first we take these examples and do some consistency analysis to see where examples contradict one another, okay? And separate these examples into pools. Inside each pool, we don't have inconsistency. Everything is consistent, okay? And then for each pool, we apply the genetic programming learning, okay? On only the examples that are in this. The same for the others. Then we take all the rules that we learned, we merge them all together, and then we try to refine these rules to have the final setup. Okay. By doing this, we could have a search space that is a bit larger. So considering this string arithmetic, some functions, operations that we could inject in our coding, and this allows us with working with these small examples and consistent, so we don't have to restart on the consistencies. And at the same time, resolving the consistencies is done at that step. Okay, so we have these pools. From the pools, we generate rules. We merge the rules. Then we try to refine the rules. So these contradictory rules after merge, and we use a simulated annealing process. And the things that we are doing, we never change the conclusion of the rule because the rules produce the right things. What we need is to inject some additional conditions to differentiate from one situation to another situation. So this simulated annealing process just try to inject some conditions. Okay, an example, I have these two rules, exactly the same source pattern, but different conclusions. Okay, so in one, I just create one table and concatenate the names of the two tables, and the second, I will create a separate table. Okay, and so the only thing that I do is to inject these additional conditions that check that the tables that I concatenate the tables, I need that one of the classes does not have more than one association. Okay, so this is a way of injecting these conditions and to improve our rule set. And these are an evaluation that we did with some transformation problems. So this is the average precision and recall in the pools. So very good one. Then we merge the rules, and then the precision is a lot. The recall is good because we always obtain the right things, but the precision is not good. And then we did this refinement step, and then precision came back to the level or sometimes better than the one that we had. Okay. Okay. So this is the last example. I try to go very quickly. So this is how to learn API usage temporal patterns. So I will explain why we need to do that. So usually when you use an API, especially something that is specialized, not like JUnit or so on, even JUnit or other APIs. So you have sometimes, you never use one method only. So usually you have to use a set of methods in a certain order, okay? But you have in an API, you could have thousands of public methods, some of them is less, okay? And you have to find yourself inside this. Documentations, usually every class or every method is documented. But sometimes you could have this global documentation saying that you have to call this and then this, and you don't need to call this if you call this, and so on and so forth. So this is, or it could be in a general documentation that will for roles and different profiles. So the idea is to We have clients within the API, and we are interested only on calls between client and API. We don't need calls between client and client or API and API, so we just need the calls that way. And if we look at the execution trace, we notice that we have some patterns in there. Each time we call this one, we call this one, for example. And the idea is to learn patterns like this one. This is the LTL formula. That means that when C is called, either A is called just after and B is never called, or A is not called just after and B will eventually be called. Okay. This is the kind of patterns that we want to infer from execution trace. Okay. So learning principle always the same with some small difference here. So we are not looking for a unique formula, or we are not trying to find a set of formulas like we did with the rules or with the welfare approximation. In that case, we just try many formulas and try to find the set of formulas that better conform to the traces. So at the end, we don't need a unique solution. We need like a set of formulas. Okay. Because this is also for recommending system. We can show them, explain them to domain expert or the library, people who wrote the library, and say, does this mean something to you or not? Okay. So solution encoding LTL formula is a tree. Okay. The leaves are the methods that are called, the idea methods that are called, and we have some either temporal operators, logic operators, or classical logic operators like and or implies. So genetic operators, these are trees, so we can recombine subtrees between formulas. And for the mutation, we can change a method that is called. We can change temporal operators, operators, or logical operators, for example. Okay. For the evaluation, we use a model checker because the idea is to, if we have a candidate set or a candidate an LTL pattern, for example, what we do is we take the model checker and we check this pattern on the execution traces and see what is the super potential number of events where the pattern could apply, what is the support, the number of times where the pattern actually applies, and the confidence between the ratio between the two. And the higher is the confidence, the more is contained in the pattern. However, we keep the three of them because we could have like if the super potential is 1 and the support is 1, so this is 1/1, and so the confidence is 100%. It does not, something that occurs once does not mean it's a pattern. Okay, so we have to keep this, and we do some intervals just to be sure that what we call a pattern is actually a pattern. This is the kind of thing that I mentioned, non-functional properties. And so we did that. The results were pretty good, but we have some limitations. The first one is the search space. So the search space, because any LTL formula applying the thousands of methods of the library is a potential solution. So this is huge search space. We could have impractical patterns, so large LTL formulas. So this is why we divided this space between impractical, something that too big that does not mean anything. We have this machine usable, which is like a more controlled one, so we could automate. And we have this humanly understandable, because a logical temporal formula is horribly difficult to understand, even small ones. Okay, so and if we want to validate it with humans, so we have to limit ourselves to this. If we are confident that we want to automate it, we can take this one. And for the impractical, it could be very large, but it could be like trivial patterns, but topologies, or something that is always true. So we have to. So to solve the idea of search space, here again we use the notion of patterns using patterns. So we were inspired by the wire patterns. So we took only 4 of them, and then API usage is a combination, logical combination of these patterns. So we don't have temporal operators, only logical operators of this pattern, which makes it more easy to understand. And also we control the size. We limit the depth of the trees. Okay. So we cannot have like logical combinations. So it becomes not. So this is a way of controlling the space. But the results, these are for each. We have like 8. We have 8 APIs with 45 mobile apps using them, and we look at we divided the traces into 2. One, some traces to learn the formulas, and other traces to test that on unseen clients. And if we look, so we usually we have a good generalizability. So the patterns that we find in some clients applies also to other clients, except for this diversity. And this is just the confidence. What we plot is the distribution of the confidence on the learning set and the test set. We also look at if these patterns are meaningful. So I show here 2 examples that are completely meaningful and sound, but they were not in the documentation. Okay. So for example, in a database, if after calling update you call close, then you cannot use the on open, for example. And sometimes we also have this. So when you have queries and you have results and you compile them, you cannot compile again. Interesting. So I'm almost done with the presentation. I just want to thank the members of the GEO team that worked on these topics. So some of them were involved in the how to use multi-objective optimization to learn software artifacts. So former students, current students, and colleagues. And also we are working a lot now on some of the ideas also come from our work on how to repair software artifacts using also multi-objective genetic programming. So just to summarize, I talked about automation, how automation is important, and how this automation is difficult for domain-specific artifacts. I showed that we could have a 2-step process when first we obtain examples, then we derive knowledge from these examples. I show for 3 different examples of problems how we could apply this approach, and how the approach could have some limitations, and how we could improve our work to cope with these limitations. And yeah, so that's all from my side, and then we'll be happy to answer questions. So the first one is how to treat the knowledge. We must be aware of some the examples of the knowledge can be multiplied. Yes. So how well and how the knowledge. Yeah. We do not deal with that problem because we see it in 2 different ways. Either the things that we learn, we give them to humans to validate them or integrate them. So we suppose that once they have this artifact, probably they will modify them, perhaps, and so on and so forth. So we cannot rely on this learning process to maintain them. That they could be eventually, some of them will be removed, others will be. The second way of seeing it also, we could adapt these techniques to be incremental. So we already rather than starting from a randomly generated populations. So we could start from the population or some of the population obtained from the initial set of examples. And if we have new examples, we just rerun the process starting from this population rather than starting from a random population. Yeah, yeah, that could be a possibility. Yeah, that could be a possibility. We didn't work on this, but yeah, definitely. For example, if you have like two set of rules, we have this rule of different situation, or if you have a language that is like a sub language of another language, so how we could combine this within this. Yeah. So, oh, in fact, if I talk about the rules in general, well being like welcoming rules or transformation rules, so an example could be involved in many rules, and one rule could involve many examples. So we don't have like a one-to-one relationship between examples and rules. So this it depends, and usually this is a very important problem. For example, when the last thing I talked about is what we are working now on how to repair artifacts, and one of the things that I showed a bit before. Yeah. So Sahara and Jesse, we are working on how to repair errors in model transformation, model transformation. And the one thing that we are facing today is, so we don't want to repair one error at a time because there could be some interference between the errors. But we noticed that when we have 3 errors at the same time, we can repair them. But when we have like 4, 5, 6 errors at the same time, 8 errors, so we still having problems doing this because sometimes this is like a diversity things that we are also trying to apply. So sometimes you have a statement where you have 2 errors. Okay, you have one error that is repaired in the statement. So there is a solution that repaired one error, but the other error is not repaired. So this solution is ignored because the statement still produce bad results. Okay? And so we are working on how to, not in the example themselves, but in how to inject diversity with respect to the errors. Okay? And so we are working on this, but this is still
So I have a question from online. This is from Max. So Max is asking, to learn from a statue, you must be able to run the user program because of the extremely wide variety of data usage. Must be set for many user applications. This takes an unusual amount of time. How does the approach scale for
let's say the client that we use. So we have some APIs and we take some clients. So there is something to do with the clients. So we don't need to have, and as we mentioned it in the results, with the subset of clients, we inferred some patterns that we found that work for other clients. So we expect that if some patterns are important, so few clients and within the same client, a few use case scenarios, for example, could be like the test cases and so that we need for executing the application could be enough. But the other thing that I can add is we are not learning these things every morning. So if we have an API, and if it takes us 1 month to run the clients and learn this to document the API, this is okay, because the performance depends on how much time you run your approach. In our case, so we do this once 6 months or things like that. So the performance is not really an issue. The away from this group. Yeah, exactly. We didn't use social diversity. I mean, the sampling is very important. So usually with the IPR we use clients that we know these clients are safe, because we can also, for the clients, look at the bug reports and the issues and things like this. And if you find a lot of issues related to the IPR, so this is a bad sign. So we have to do it. But yeah, the sampling is very important. Yeah, exactly. In fact, what we, not for this problem, but for other problems we are working on, we look at the commits before and after, okay, and we try to learn what happened. Knowing that the case before, the situation before, when we learn what happened after, we look at how errors were corrected. Is a way of also.
To my understanding, the dream is basically use this search data over here. This will actually eliminate my search data. This is hard to actually discover the
It depends. Let's say it depends on how we define search space, but also on the example that we have. So if the examples are not very business knowledge, so we cannot discover it. So this is why also the quality of the solutions that we produce is modulo the representativeness of the examples. So the more the examples are representative, the more the solution are good. But also there are some complex things that you cannot find. So for example, you cannot learn a Java program like 1,000 line or 10,000 line Java program that solve the problem. This is too complex. So for the moment, we learn like specialized model transformations. And also, this is a piece of advice for the student. As a researchers, we are not trying to advance the state of the practice. So sometimes yes, but we are trying to advance the state of the art. So sometimes the work we do is not scalable, for example, to real life problems, but still this will nourish the next researcher and so on and so forth. And so I believe that what we do in research should solve an NCR problem today. Should not be, it could be a criterion, but should not be sometimes we need to advance the state of the art with some new ideas. And even if they cannot solve like large scale problems, still someone else will just start from this and try to improve.
I guess there's no more questions. Let's have the speaker.
Stop sharing. Okay, so it's should I leave?